There we go. So should be recording now. So if you're joining us virtually in this recorded space, welcome. So I just did a poll unscientifically of some topics people want to cover. It seems like chapter 15, lots of people want to look at. A little bit of fluid flow as well. And then I have some other replies. So Owen, can you tell me what M value in which section? So I'm guessing you're talking about the M values in the wave optics, like in chapter 18, where we use that to kind of represent which mode we're looking at. Okay, very good, very good. So we can definitely talk about that when we talk about waves. Let me make a note of that. Okay, and then I got a few general questions, which we could actually start with. So what kinds of conceptual questions are going to be on the final? This is a very good general question. So in my opinion, you should always be thinking conceptually, even when you're doing calculations. So I don't see these things as super separate. And with that philosophy in mind, the way that I structure the final, and I'm still editing it because I want to make sure that it matches everything I've told you and that it's, I think, fair and, only relies on the sections that I highlighted. So it's still a work in progress. I'm having some people test it out. But anyways, the philosophy guiding me there is that primarily I want you to be able to first calculate something and then explain what it means, right? So for example, you might have to calculate some fluid flow in a problem related to chapter 9, but then I might ask you to interpret, okay, how, does this fluid flow, how long would it take to fill some characteristic container? Like how long would this arterial flow take to fill up, the first atria of the heart or something like that? So, or maybe the conceptual question could be more of the nature where you're sort of asked something like in wave optics, why do we get interference patterns, right? So you could be asked to calculate an interference pattern for a double slit or a diffraction grating, something like that. But you could also be asked, why do we see that? Why and how is this or how is this distinct from ray optics where we don't see interference patterns? When would you use one or the other? So that's what I would be thinking about, sort of as you go through the quantitative side of your practice for the final, always ask yourself, why is this happening? What is the meaning of each of these terms, of each of the variables in your equation? And then what is sort of the end goal here, not just with your calculation, but why did people develop this? That's a nice conceptual question to have in mind because it often elucidates these connections between seemingly disparate topics. So, okay, but without me getting too philosophical here, let me then go ahead and pull up some questions from chapter 15 because I do want to focus more so on working through some problems, some example problems together so that hopefully we can get the most use out of this session. So, okay. Let me know if you can't see my screen share now. But so these are some past examples from 3D. Thank you to Professor Guerra for sharing these. And I could post the ones that we work on today, but I don't think I'll be able to provide solutions since he didn't provide them, other than for the ones that we work through together. So unfortunately, I think that's just going to be the reality based on the timelines involved here. But anyways, so I think we really haven't gotten to do much work with pendula. So I think it would be good to maybe do problem 2 here if you want to look at chapter 15 material. And so chapter 15 on oscillations, and here we have an oscillating system. We have a pendulum with a string length of 1 meter, a massless string, so that just means we don't have to think about those physical pendulum calculations with the moments of inertia. We can just use the basic formula. At t equals 0, it's released at an angle of negative 10 degrees. So theta of 0, which is our initial condition, is negative 10 degrees, as shown below. Assume that for oscillations of the simple pendulum, sine theta is theta. So that, again, this is the kind of detail that if you read through the textbook, you'll understand why this is stated here, but it's basically just telling you that you can use the formulas from the book. So this isn't anything weird. Saying we can take advantage of the small angle approximation, sine theta equals theta, in radians, that's true, and ignoring friction. So it's not a damped oscillation, it's just classical, perfect, simple harmonic oscillator. So the first question is, what will be the angular position theta at 2.67 seconds? So to answer this, we need to actually get the functional form theta of t. Okay, and so this involves, using our initial conditions to figure out, is this a sine, a cosine? Is there going to be some phase shift? And what is our angular frequency? What is omega? Okay, so to answer this, we can start off by getting omega, and this is one of the formulas that I would encourage you to include on your formula sheet. So this is, something related to a square root. And remember, I think many people can remember the spring one, which is root k over m. And so that's telling you that something about the springiness, so that the angular frequency is something about the springiness over something about the mass. And similarly, here, the g is telling you about the restoring force here, which is just coming from gravity. And the L is telling you something about the resistance to change of the system, or the scaling, however you'd like to interpret it. Okay, so we can just plug in 9.8 and 1, and we get, I don't know, whatever root 9.8 is, some number. So I'll just plug that in my calculator quickly. It's close to 3, yeah, 3.13-ish. And this has units of radians per second, an angular frequency. Whenever we use any of these square root formulas, those will be the units of omega. And now we just have to ask ourselves, okay, we have our theta of t. We don't have an initial velocity, right? Our v of 0 is just 0. So that's telling us that we want something like a cosine. And the reason for that is that a cosine graph at time 0, so if this is the t-axis and this is our theta axis, the cosine graph starts off horizontal at some extended angle, and then proceeds to move, converting potential energy into kinetic energy. But typically cosine at 0 is 1, so we need to scale this, right? Here we start at negative 10 degrees, so we actually want to use a negative cosine, and we just put that negative 10 degrees out front. And then we have our omega, 3.13 times t, and we don't have a phase because we've already taken care of that by choosing our negative cosine. So if we'd wanted to use sine, we could have done so, but we would have to have some pi over 2 phase factor to shift our function appropriately. Okay, and now we can just plug in this time into this problem. And then be careful here. When you're working with a pendulum, these problems are often tricky, but this is realistically how this works. Your amplitude, so the theta, the angular position of the pendulum, is often given in degrees. And that's okay, but your calculator should be in radians mode here, at least for this part, because this 3.13, our omega, is in radians per second. So when we multiply by a time, the argument of the trig function will be in radians. And then that will turn into some ratio, right? When we get a cosine, that's just an adjacent over a hypotenuse of some triangle. And so our final answer will be in degrees, since there's a degree amplitude up front. Right? And I know this is a little confusing, but that's why I want to really highlight it. So if we do negative 10 times cosine of 3.13 times 2.67, I get that this is negative 4.8 degrees. So after this amount of time, 2.67 seconds, our pendulum is somehow at a position here. Okay, so it may have made multiple cycles. We can't tell from what we've done so far. And in order to know that, we would have to convert this angular frequency into just a standard frequency. And then we could think about what the period is for our system. So then we maybe need to start doing that, because part B asks, will the bob attached at the end of the string, so the bob is just the mass, be moving to the right or the left of the vertical at this instant, 2.67 seconds. So to most directly answer this question, and I'll change colors here, we just want to look at the velocity equation for a pendulum, which as we've seen is, so we write it sometimes as theta prime of t or v of t. These are equivalent. So this velocity equation is just the derivative. And so if you can take a derivative, then that'll be easy to find for you. But if you can't take a derivative, then you should just remember that for a cosine x function, that becomes a negative sine v function. And so here, the negatives cancel out front, and we have 10 degrees times this omega times sine of omega t. And we have to be a little cautious with our units. So even though we seemingly have radians and degrees here, that's okay. I mean, at this level, they're just asking for if it's moving to the right or the left. So all that we really have to do is plug in this time and see, is sine of this omega t positive or negative? And we see that if we do 3.13 times 2.67, that we get a positive sine value. So this is some positive number. And that's enough to tell us that we are moving to the right. So we've defined to the left as negative. So this is moving to the right. So that's all that you really have to do for this part. You could also just calculate the period of this system, right? So the period is going to be 2 pi over omega. If we first convert omega to a frequency, and then we do 1 over that frequency to get a period. So we could quickly find that number just to give some context. So that tells us that our period is about 2 seconds. And so after 2.67 seconds, we, let's see here. This is, interesting. Maybe I made a mistake. So this is why it's good to check. Let's see. Cosine goes to negative sine, and yeah, sine of 3.13 times 2.67 is positive 0.88. Omega's good. Interesting. Okay. I might be making some sort of algebra error here. So I guess that's the trickiness of these problems. Okay, so just to go back through then, for part A, we found our theta of t using our initial condition. So at t0, we get negative 10, which is good. And we have a cosine because we don't initially have velocity. And we have the right omega, root g over L. Oh, that's a good question. Thank you for everyone in chat. So in part A, we could call that positive, but that would just flip all of our signs, because then we would be calling angles to the left positive, And so if we're moving to the right, in that case, we would be moving in the negative direction. Right, because we want to have some situation we want the situation where if we have t of 0, that this thing would be 1, which is true. And then the initial angle at time 0 would be negative 10 degrees. So that equation for theta of t looks correct to me. And then if we take a derivative of that, just to simplify what we're having to do here, so the derivative of cosine is negative sine, so that will cancel out the negative out front. And omega is positive, so the only thing that could change the sign here is if we, sorry, I see what's going on. I was just not interpreting part B correctly. Okay, so everything's right that we've done so far. But when we find this period is 2 seconds, what that means is that the pendulum swung from the left to the right and back. So it would be back at its original position after 2 seconds. And then if you let it swing for an additional 0.67 seconds, then it would be very close to the center, but it would, which is what we found in this part. So it would be pretty close to 0, over halfway, but that it would be traveling to the right. So I think this all checks out. But I'll go over it when I'm not being recorded, I guess, and make sure and let you all know if it's not the case. So anyways, then moving on to part C. So the answer for part B then would just be to the right, I believe, from what we just calculated. So then moving on to part C, the second instant where theta is plus 2 degrees. So for this, we want to use the approach that I outlined in that trig interlude slide from chapter 15, which is good to look over, where we have a cosine function, and it has a negative amplitude, but that's not too important for what we're doing here. Basically, this cosine function is symmetrical about 0. So we'll find the first solution, which will be, some positive number, and then we'll take the negative of that to get the other branch of the solution. So the one that's, increasing if the first is decreasing or vice versa, and shift that by factors of 2 pi over omega to find the first and second physical instance where this angle is occurring. Okay, so using our theta of t equation, which is the basis of all of this, right? That really contains all the information for the system. We just have to interpret it. We can go ahead and start inverting it. So we put a positive 2 for our theta of t, and this is equal to negative 10 degrees times cosine of omega t. And so our t will just be 1 over omega times the inverse cosine, which our calculator can provide for us, of negative 1/5. And you can see that we had degrees on both sides, so those cancel, which is good. We're taking an inverse cosine, so that should just be our argument should be a dimensionless number ratio. And so now we can plug that into our calculator and see what we get. We want to make sure, again, that our calculator is in radians mode, so that the radian value we get from the inverse cosine cancels with the radians in our omega. And when I do that, let's see what happens. I have inverse cosine of negative 0.2 over 3.13. So I get 0.57 seconds. So that would be the first, this is the first time that this occurs. And then to get the second time, T1, to get the second time, what we have to do is we have to first take the negative of this, so negative 0.57, and that'll get us, another solution, a valid solution mathematically, but it's not physically useful because it happened before time zero. So it was before we released the pendulum. So it's just an artifact of the fact that we have this infinite function, that expands in either way. So to get a physical solution, we have to take advantage of the fact that it's periodic. So we add the period, which is in this case 2 pi over omega, just like we set up here. Okay, and so in this instance, we find, so if I just do this quickly, (1.44) seconds. So this would be the second time that it's at a position of 2 degrees to the right. Okay. And if we wanted to find the third, we would have to take this t1 and add 2 pi over omega to that. So just to see what would happen there. So that would occur at 2.57 seconds. And that's what's weirding me out a little bit here. I feel like I did something wrong in that first calculation. Let me see. I forgot my minus sign. Sorry, this should have been plus 4.8 degrees. I think that's what's been confusing me this whole time. Okay, so if I had just typed in the numbers correctly, plugging in 2.67 to our theta of t, we should get positive 4.8 degrees for answer A. And then that makes more sense that at 2.67 seconds, which is a little under 1.5 periods, we would be on the right side of the equilibrium, moving to the right. Okay, glad we got there eventually. And that's the nice thing about these multi-part problems, is you can sometimes catch your mistake along the way when things don't make sense. But anyway, so these are our first and second solutions, which tell us the answer to part C. And then it asks, how long does it take for the blob to make 6.25 oscillations? Well, this part is actually quite nice because we already have our period up here. And so we just have to say a period is the number of seconds per oscillation, so per cycle. And so we just have to multiply that by the number of cycles that they want us to know here, which is 6.25 cycles. And that'll give us some amount of time. So just 2 times 6.25, that gives me 12.5 seconds to make that many oscillations. Okay, so just to recap, the way that we solve this problem is we find our omega using root g over L, and we use our initial conditions to get our theta of t, which in this case is -10 cosine 3.13 t. And then we can, for part A, hopefully better than I did, plug in our 2.67 as t and find a positive 4.8 degree location at that time. We can use our velocity equation to figure out if it's moving to the left or the right based on if that's positive or negative. And I see a question here about why is it that we don't have to convert that 10 degrees into radians since everything else is in radians? So what I would encourage you to think about here, it's a little confusing, is for the springs, that amplitude would have been in meters, okay? And so the dimension of the units on the amplitude don't have to match the units of omega or in the argument. And even when we find the velocity, right? Remember that the velocity in the case of a spring, like the maximum velocity, for example, is a times omega. So that has units of meter radian per second, but the radian doesn't really matter. And so it's strange, I agree, but you can totally have your amplitude be in degrees even if you're doing the whole rest of the problem in radians. And you can see that even in part C, where you would think that it might matter because you're doing, you're using trig functions and you have degrees in your equation, we have a 2 degree on the left and a negative 10 degree on the right, and so those units will cancel as well. And we just get negative 1/5 as the thing that we have to take the inverse cosine of. So it turns out it works. If it makes you uncomfortable, you can totally convert everything to radians. I mean, honestly, that's what I tend to do when I'm actually having to do problems like this for my research or something, is I just like to use only radians because they're you know by far superior. I don't know, maybe not, but it does make things feel nicer, but it's not required. I personally don't care about sig figs in the way that the homework does. So this is another chat question. I would just say, to be reasonable, usually if you give, a couple of digits worth of accuracy the way that it is in the quiz, that's sufficient. So don't just round everything to like, the nearest 100 or something, but there are ways to round things that take away so much information that I can't really grade you. So if you're in doubt, just leave more digits, whatever. That's okay. Why is the 10 degree positive in the velocity equation? So that's coming from the fact that if you look in the book, so if you're not familiar with calculus, if you just look in the book, what you should notice is that if you're using a cosine for the position of an oscillator, that like a positive cosine, that the velocity equation will be a negative sign. And if you understand calculus, that's because the derivative of positive cosine is negative sign. And so here we have a negative cosine as our position, so that becomes a positive sign as our velocity. I know this is maybe a little tricky, but it's good to see how that works in this case. And in the case of a position function characterized by sine of omega t, there's not a plus or minus shift. So be careful with that, is what I would say. Any other questions about this problem? So this has taken a little while, but hopefully the level of detail is helpful as you study. I do plan to post the solutions for the midterm that's on Canvas. I just have been really wanting to get your grades for the project done as quickly as possible, so that's kind of been the main thing, and answering emails and making the final and so on. Okay, so then I think that's a good representative question from chapter 14. I know there were some people who wanted some stuff from chapter 9, so let's try a question from there, and I'll try to get through it a little more efficiently maybe, but maybe not so efficiently that we lose all helpful information. Okay, so here's a sheet of some extra examples for chapter 9, and like I said, I can upload these to Canvas, but I won't be able to provide solutions to these extra examples other than what we talk about today. So I think I feel like these density ones or buoyancy ones tend to be a bit of a slog, and people tend to do really well on them. Maybe number 3 is good. So we haven't had much practice, I think, with Bernoulli's equation. So let's look at this first. So the figure below shows how a stream of water emerging from a faucet necks down. So that means that the stream tends to look narrower. And you can try this yourself. Go in the bathroom and turn on the faucet. You'll see that it starts off wide and then looks kind of narrower as it falls. The cross-sectional area A is 1.2 square centimeters at position A1 and 0.35 at position A2 as shown in the figure. The two levels are separated by some vertical distance, 45 millimeters. The question asks, at what rate does water flow from the tap? So this is a good combination one, because we have to think about Bernoulli's equation and the way that there's some, potential energy funny business happening here. So let's write down, so, we see a fluid flow question. A common thing that I'm asked is, how do we approach these? We see a fluid flow question. It doesn't tell us anything about viscosity. So this is going to be an ideal flow situation. And so the only equations that we really have here are, so we know that the flow rate, A1, V1, at position 1. So we can always say that the flow rate is the cross-sectional area times the velocity. And we also have something to the effect of Bernoulli's law, which is that our pressure plus 1/2 rho V1 squared equals our pressure at some other point plus 1/2 rho V squared at that point. And so for ideal fluid flow alone, these are the only two equations that we have that actually characterize such a system. And now it's our job, once you get that information from your formula sheet or whatever, it's our job to figure out how we can actually use that. So you can see that using the fact that the flow rate is equal at different points, right? However much fluid is flowing through this upper surface, the same amount has to be flowing through the lower surface. If that's not the case, then we would have fluid backing up somehow or compressing or something like that. So the flow rate has to be constant for any chunk of this, which means that as this gets narrower, we expect the velocity to increase for ideal flow. This is the situation. So we can write that, let me switch colors. So now we're looking at this problem specifically. We can write that A1 V1 equals A2 V2, statement of fluid continuity. And they tell us our A's. So this actually means that we can write a ratio of velocities. So we can say that V1 over V2 is A2 over A1. And they tell us these numbers, so we can actually plug in. Let me do this for us. So 0.35 over 1.2. And we get something very close to 0.3. So I'll just round that for this, but you should try to save digits in your calculator as you go to make your life easier, just in case something is very sensitive. And so that tells us what we expect, right? That the velocity at position 1 is slower by a factor of, 30% of the velocity at position 2. So as it gets narrower, this is speeding up. But they want us to say at what rate does water flow from the tap. And so what we need to do is we have to go a little bit further, and we have to ask, what is causing the change in fluid flow here? And so we can think of it as a pressure difference, as a dynamical pressure difference, and use Bernoulli's equation that way. But I think it might be actually easier to just directly say that this fluid is in free fall. So its velocity at position 2, if we think back to 3a, is its velocity at position 1 plus a times t. So that's one kinematics equation. But they don't tell us about the time here. So instead of using this one, it's nicer to use something that directly takes into account this height, which they do tell us is 45 millimeters. So we can instead write that V2 squared is V1 squared plus 2a h. And this gives us our second equation for the velocities. So we can plug in. So if they want us to find at what rate it's falling, so we want to actually know V1. So we can rearrange this and say that V2 is V1 over 0.3. And then we can plug that into our equation here to solve for V1. So V1 over 0.3 squared equals V1 squared plus 2. Our acceleration is 9.8. You could say negative, but then your h would also be negative, so that those would cancel out. So I'll just write this as positive. And then 45 millimeters, we want to be sure to convert that appropriately. And we haven't chosen units in any way here, since this 0.3 is unitless, it's just a scaling factor. But our 9.8 does have units of meters, I suppose. So we should just convert this to meters, 45. times 10 to the minus 3. And this lets us solve for V1. So it's an equation with quadratic factors, but we only have quadratic terms in it. So we don't have to actually use the full quadratic equation here. We just need to get all those V1 squareds on the left, for example, and factor out any shared factor, divide by that, and we can get our answer. So just to do that, so we have 2 times 9.8 times 45 times 10 to the minus 3. That'll be in the top. And then in the bottom, we have 1 over 0.3 squared minus 1, right? Because when we solve this, we'll have V1 squared times 1 over 0.3 squared minus 1 squared, which is just 1, equals the stuff on the right-hand side, 2 times 9.8 times 45 times 10 to the minus 3. So at the end of the day, I get 0.087 meters per second here for the speed leaving the top. And then they ask at what rate does the water flow from the tap, which is a little bit of ambiguous language. In the final, I'll try to be more clear about what I want in these sorts of instances. So I'm going to interpret that as they want Q, because Q is the flow rate, and they ask what is the rate that it flows. But it's ambiguous because velocity is a rate of its own. It's a distance over time. But anyways, so in that case, then we just have to multiply this by A1, and we need to make sure to convert A1 into square meters. So we would do 1.2 square centimeters times 10 to the negative 4, since it's squared unit. We have to be careful. And then times this, and we get roughly 1 times 10 to the negative 5 cubic meters per second for the water flow rate coming out of the tap. Okay. Oh, and I got a question in chat. What time is our final on Tuesday? It's just during class time, or when it would be, so 8 to 9:20. Very good, very good. So any questions about how we approach this problem? So I didn't end up using Bernoulli's law, I guess. But if we were to use it, we would just want to use the fact that there's some change in height here. So we can have a rho GH on either side, or I can just write it. So we could have a rho GH1 on one side, a rho GH2 on the other, but when we combine them, we can have that delta H, which is what is 45 millimeters in this problem. And the pressure is just atmospheric pressure here. So these P1 and P2 would cancel. And you see that when you do this, you actually get this kinematics equation. It's quite nice, right? Because our rho's cancel from each term, and then we can move the 2 to the other side. And so we get, so I have to be careful here. V1, we get V2 squared equals V1 squared plus 2GH. It looks like you would get it the other way around, but you have to be careful with what you call the sign of H. And so the way that I wrote it in green, H would be negative. So when we get it to the other side, we would get V2 squared equals V1 squared plus 2GH. But you can see this is just a kinematics equation. So, it might be nice to have the kinematics equations on your formula sheet, but they should all be derivable in the situations you need them. Okay, other than you should know V final is V initial plus AT, which is sort of the definition of acceleration. But other than that, they should be something that arises from Bernoulli or other situations. Anyways, a bit of a rambling into this problem, but are there any questions on how I approached it or what you should do in this situation? Okay, so we've still got a decent chunk of time, 20 minutes or so here. We've looked a little bit at chapter 15, a little bit at chapter 9. Let me scroll back up. Okay, so people wanted to talk about wave optics. Let me refresh myself on what I said might be included in that before I get off on too much of a tangent. But yeah, so I'm answering more questions from the chat. The real final is pretty similar to the practice final. Of course, if they're not identical, and like, for example, the practice final has a question about, blood flow. So that's not a guarantee that there will be a blood flow question in the real final, but you should expect to be asked things about ideal fluid flow, viscous fluid flow, maybe even, hydrostatic pressure, the whole rho GH business. So in that sense, it'll be very similar. And I think the level of difficulty should be similar as well. And if you're not aware, I did post the practice final solutions, and I typeset them and everything, so hopefully they're readable. But 1 second here. Okay, so in my announcement, I said that we're only doing sections 18.2 through 18.5 from the wave optics material. So opening the book here. So that's thin film, double slit, diffraction grating, and single slit. And this ties in, I guess, to the question someone had about what IM is. Yes, so to answer another question, that list that I posted as an announcement of the sections potentially on the final is complete, except you're right, the chapter 21s, I can go back and edit that announcement. So now you only have to worry about section 20.1, yeah, the lenses in combination. So I was planning on asking you some questions about, microscope magnification, but I won't, because we didn't actually cover them, and I don't have time to record an extra lecture, and I'm sure you all probably don't have time to watch an extra lecture. So just to be fair, I won't ask you anything from there. But okay, anyway, so going into chapter 18, I don't think I have any extra problems on those. Maybe I do. Let me see. Yeah, I don't. Unfortunately, Guerre didn't cover that in much detail, but I can open up the book and we can do some problems from there. So while I'm doing that, let me look at the chat. So yes, there will be a seating chart. I probably won't release that until Sunday because there's lots of things to do, to be honest. I'm sorry that some of this is a bit slow, but that's a good question, and I do plan to make a seating chart just because I think that makes it a little more orderly and a little bit more of a deterrent, to cheating, obviously. So anyways, looking at the chapter 18 problems, I'll take a break from the chat for a minute. Did people, I guess that there are a couple of categories. So you saw a thin film practice problem in the quiz, and I'm planning on, once a couple of people who had makeups take it, probably tomorrow, I'll release the solutions to that. So you can see a worked example of thin film interference. So maybe it's good to do one of these double slit problems. Let me zoom in a bit here. So let's try out maybe problem 13. Okay. Let's try out problem 13 here. So we have two narrow slits that are illuminated by light, a wavelength lambda. We have a double slit problem. Okay, if you hear something like that, that's a good indication you have a double slit problem. The slits are spaced 20 wavelengths apart. Okay, so this is a fun problem where we're going to measure things in wavelengths. So D is 20 wavelengths. What is the angle in radians between the central maximum, which is often the M equals 0, that's what's used to label that, and the M equals 1 bright fringe, so the first order fringe. And so getting to the very early question about what is M, so M is just a way to number these bright spots. Okay, so we know that for a double slit, so if you take your razor blade and cut two little openings in a sheet of paper, shine a laser on it, you have a double slit. You can make it that easily. You let that light project onto your wall, and you'll see a bright spot in the middle, and then there'll be dark spots on either side. Bright spots, dark, bright, expanding out, and it'll get a little bit less intense as you go out in either direction until eventually it just kind of trails off and you can't distinguish the two. And so this M number is just a way of talking about which bright spot you're wanting to tell someone is interesting in some situations. So the M equals 0, that's referring to the central one, and that's, as they do in this problem, often called the central maximum. And then M equals 1 in the book, they use that to describe the spot to the right and the left. I mean, it is symmetrical, so that's okay. Some books will call the one to the right M equals +1 and the one to the left M equals -1. I think that's actually a bit better notation, but that doesn't match with what the book does. So you can do it either way. But anyways, so for this problem, we're looking for the angle between the central bright spot and M1. And so this is just theta 1 in the notation that we use in the formulas here. So these theta angles, if we have our double slit, so two slits right here, we look at the interference pattern, we have the central bright spot, and then we have all of the higher order bright spots on either side. So the central one is M equals 0, and what they call theta is just the angle relative to that center line. So this would be theta 1 if this is pointing to this M equals 1 bright spot. So that's all they want us to find here. So to solve this problem, what we have to do is we have to go back and look at our formula sheet. So we can just scroll back up here to the summary page really quickly to see it. And so for double slit on the left here, they show you a picture actually of what the wall would look like when you shine a laser through a double slit. And they tell us that theta m is just m times lambda over d. And so that's a really nice formula. So we'll come back down here. Okay, so theta 1 for a double slit is m lambda over d. And they tell us we're interested in m equals 1, the first bright spot outside of the maximum. And we don't know what our lambda is, but we know our d is 20 lambda. So these cancel. And when you use this formula, the answer will automatically be in radians. So this is true of any of the formulas in the book that are giving you an angle, unless they say otherwise, which I don't think any of them do that we've covered, then the angle that will naturally be output by these sorts of things will be an angle in radians. So 1 over 20, this is like 0.05, I believe. And so that would be your answer. Okay. So this is a pretty direct one, but they're keeping everything in variables. So I know some students struggle with that. But honestly, I think it's good to practice these problems where you try to keep everything in terms of variables, because even when you're dealing with actual physical values, staying in variables until the very end can be really beneficial in terms of checking your work, making things neater, so you're less likely to make a mistake, and generally just, keeping you more organized. And so you can see in this situation, you don't even really need to know what to plug in for lambda because your lambdas cancel, at least the way that they parameterize d. And that often happens as well. So you'll be working with physical values, but sometimes things that you think might matter actually cancel, and so you don't even need to use them in the end. And that might be an example of a type of conceptual question that you could be asked, which would be sort of, here's some situation where you have to do a calculation. If you wanted to do this calculation, if you wanted to find theta 1, what do you need to know? And so you don't actually need to know lambda and d separately. You just need to know how they're related. So if you know that d is 20 times lambda, that's enough to find the angle. But you don't need to know the exact numbers. So 20 times lambda, if we want to convert that into nanometers, we can't do it. We'd have to know specifically what lambda is. We only need to know that ratio. And that's evident in the formula, perhaps, since it just depends on lambda over d and not any of them separately. But anyways, I digress. So are there other wave optics questions that people would like to go over, or look back at what's happening? Very good. How would we word it, or how would a problem word it? And this is a great way to conceptualize your studying, to try to think about what they could ask you and see if you can answer their question. So I'll bring this stuff back. So how would they word it if you were supposed to find the angle between the m equals 1 and the m equals -1? So I'm just going to call it m equals -1. Oops, sorry, this color is not great. I'm just going to call it m equals -1, but basically it's the first order bright fringe on the other side of the central maximum. So the way they would word that in the style of the book would be, find the angle between the bright fringe on either side of the central maximum, something like that. And if I were to do it, I would probably do it in a similar way, sort of, what is the angle? Yeah, something like what is the angle between the bright spot, or between the two bright spots that are on either side of the center. And so to do that, you would just double it, basically. Or alternatively, if I asked you to find the angle between the first spot on the left and the third spot on the right. So what you would have to do in that case is first you would find θ1, then you would find θ3, just using this formula up here, and then you would just have to add them up if you wanted to find the angle from the first bright spot on the left to the third bright spot on the right. You can see how you can just nicely combine these quantities. And yeah, so you could solve that. In the case that it's symmetrical, you could just multiply your value by 2. If you just wanted to find the angle from the second bright spot to the second bright spot, you find θ2, you multiply it by 2, which is the same as adding 2 θ2s together. So very good, very good. And the other interference patterns that we saw in this class, so just to go back up to the summary page. So all of these interference patterns are symmetrical. So the ones we get from double slit, diffraction grating, and single slit, they're all symmetrical. So if we find a theta or a y value for one side, it'll be the same as that for the other side. And then we didn't even really talk about how to get these other bright spots for circular aperture. And I actually think I'm not including that, huh? Let me see again. So I said 18.2 through 18.5. So yeah, but we're only going to single slit diffraction, I guess, on the final. So you don't even need to worry about the little target logo here. But it's it's a very cool phenomenon, circular aperture. And like I said, you can measure the diameter of your red blood cells. If you take a dry sample of blood and shine a laser through it, you can, which I've done myself, you can use this pattern that you would see and measure that central width, for example, and calculate your diameter. But anyways, so all of these diffraction patterns then are very similar. It's just for double slit and the diffraction grating, they're literally identical, other than the fact that they've become narrower as you have more evenly spaced openings. And for a single slit, we actually don't have a formula for the bright spots. We only have the formula for the dark spots and for the width of the central maximum, which is really just very similar to what you're asking here, right? So if we say that the dark spot for the single slit is to the left by some amount, then if we just double that, which is why there's a factor of 2 in this equation here, then we get the width of the central bright spot. But yeah, so in that sense, all of the types of interference patterns that you might be asked about on the final are pretty similar. They're all just light and dark spots symmetrically spaced around the center. There's central maximum for all of them, and it's just a matter of the details. And those are all characterized by the formulas that you have. Okay, so hopefully that's helpful in regard to chapter 18. Oh, I have a question here. How do we distinguish between a diffraction grating and diffraction problem other than their spacings? So I'm a little confused on that question, so feel free to type some more to clarify. Oh, a diffraction grating and a double slit. Okay. So you can see that in the book, and I really don't know why they do this. So the equations for the two are actually identical. It's just that they don't let you use the small angle approximation in the book for the diffraction grating. So they're not assuming in those formulas with the sine and the tangent, they're not assuming that you're dealing with small angles, which I suppose is something that's often true. You're often not dealing with small angles for diffraction gratings when you're working with something like a spectrometer that we saw in the slides. But anyways, what I would say in terms of the problems I might give you is that if you're given a double slit problem, I'll say something like there are two infinitesimally thin openings. Boom, that's a double slit problem. If I say something like you have a diffraction grating, that would be a diffraction grating problem. And so if you have the formulas for either case, then you can just use them directly, right? And the double slit formulas, since we made a small angle approximation, are much nicer. We just have theta and we have y. Those are often the two things you're asked to find, and we can find them without dealing with any trig functions. For the other two, we actually have to do inverse trig functions, right? So if we want theta m here, grab the pen, we would say that it's the inverse sine of m lambda over d. And so you can see that in the double slit, we just had that theta m is equal to m lambda over d. And those two, so they both have an m lambda over d. It's just, if you don't assume your angle is small, you actually have to take the inverse sine. Whereas if you do assume your angle is small, the inverse sine is just the identity function. It doesn't do anything. So at the end of the day, these are very similar formulas, but if I do say diffraction grating, I guess you should use the ones consistent with the book, and I'll give you credit, that way. But in terms of how they differ, it's really just that a diffraction grating is just a general double slit, right? For a diffraction grating where n equals 2, that's literally a double slit. And if you just have more and more openings that are all, as long as they're all evenly spaced, a distance little d apart, then the position of your interference pattern, those bright and dark spots, will be in the same locations. It's just that they get narrower, the bright spots get narrower, and they get more intense. And so the benefit of a diffraction grating is that you can really make these so narrow that if you have multiple colors, you can separate out the colors, because you can see how these formulas for theta, for example, depend on wavelength, so they depend on the color of the light. And so a diffraction grating lets you very accurately separate the colors of light, which can be used to tell what something is made of. If you think about those chemistry experiments where you put some boron in a fire and it turns green or something. So got a question, can we type up the notes on our note sheet or should it all be handwritten? I'm okay with you typing it up. I know that, my handwriting sucks, and I'm sure some other people's have the same problem. So yeah, feel free to type them up. You should be getting these things from your notes or from the book or from your head. So I guess I'm just, I've made up the final problems myself. So if you're able to cheat on it via knowing what the problems are ahead of time, you somehow hacked my computer, I guess. But anyways, all that's to say, sure, you can type them, you can write them on your iPad and print it out, just front and back of a sheet of paper. That's the main constraint. Yeah, I'm not going to check your sheets because, like I said, as long as it fits within the sheets, that's fine with me. So yeah, I'm okay if you put practice problems on there. I would just say that it'll fill up fast. I don't know how small you can write, but there's quite a bit of material in this class. So that's actually why I agreed to make it front and back, because I understand just trying to put all the summary pages on that much space is already difficult. But anyways. Okay, so that's about all of our time for today. I'll stick around a bit if there are any more sort of general questions or questions about the administering of the final. But hopefully this was helpful, and I look forward to seeing you all on Tuesday. Yes, thanks. Yeah, unfortunately, the final will be the full duration of class just because we have so much material. I really am going to have to, let you work the whole time so that you even have a chance to be kind of tested on a good fraction of it. I know this is sad for the people who are concurrently in 3C. So I do plan on ending it, pretty exactly at 9:20. So you at least have 10 minutes, I guess, if that's you. But I know it's not ideal. Correct. For the final, bring your calculator, which can be anything as long as it doesn't connect to the internet, and your ID, your equation sheet, front and back, and something to write with. And that's all you need to bring. I'll supply, your final papers that you can write on the front and back of if you need extra space. And it should be enough space. I mean, I'll bring some scratch paper in case people run out of space on their exam papers.